Hey everyone, here we have a Dell Inspiron 15-3531 model P28F, and it doesn't seem to be turning on. If I plug it in, I have a white light down here and then it goes out. If I push the power button, doesn't seem to do a lot. Try it again. Nothing happens. So I just removed the battery and put it back in. When I push power, it comes on and then fades out. And if we wait a few seconds, which I wasn't expecting, I just left it. There we go. 7 beeps. And if we push power, it turns off. When it's doing that, we get nothing on the display. There's quite a long time before that started beeping, so if it wasn't by chance, I wouldn't have known that. I would have probably started ripping it all apart. And yeah, but this is a clue, so I need to find out what 7 beeps means and attack that. 7 beeps usually indicates a processor problem. The processor seldom fails. It is most likely a motherboard issue. Just a couple of screws. And no, that's not a transparent hard drive, it's just a plastic box that somebody has put in the mounting screws for the hard drive. Oh, no, it's not even a CD drive. It's a blank. So how does this come apart? It's going to come off that way. Looks like the whole keyboard's going to come out from the top. The keyboard itself does come off this one here. Sometimes they hide screws under them. Let's just have a peek under the top, under the front edge. Let's see what's what. Yeah, I think that is screwed down under the keyboard. Better get that out. There we go. Come out. And yep, screws around here. Not only is our CD drive a fake, we've got an invisible fan. Now, keep plugging. Oh, it's going to almost fall out of there. You can tell when someone's tried to open them before, there's a crack through here, and they obviously had no idea that they had screws under the keyboard, so they would have been lifting and it wouldn't have been able to come up and they would have just snapped it. There we go. I can't even see a heatsink in there, so this must be a very low spec model that doesn't need one. Looks like one screw holding the motherboard in. And we've got our display connector over in the back right corner. We have to unplug that, and we'll have to take the, of course, the Wi-Fi card has to come out. What's going on over here? Oh wow. Really? The CPU's under there, the heatsink is just a thin, it's attached to this thin metal here. So it says CPU problem, but of course if it can't communicate with the CPU or there's no activity and what have you, it could just be dead. It could just be there's no power getting to it. And this is going to be our voltage regulators, or one of them at least, for the CPU because of its proximity to it. But these are, of course, like most things, they use switching regulators. So we have an inductor here, an inductor here. Each one has a couple of capacitors, and they will be controlled by, I'm picking down here, we've got a couple of FETs there, and was there any on the other side? Are they on the other side? Possibly all in one package. There's a little IC there that appears to go through the board to the inductor in that position, and there's one up here. It's quite likely this has the switching MOSFET and control all built in, which I think I have replaced a chip like that before once. So one chip doing all the work. Unlike down here where we've got, it looks like, a couple of MOSFET packages switching this inductor. That's going to be our charging inductor, I think. There's the battery connector, so I think that'll be for charging. And there's another little inductor for something else. So yeah. Okay, so on the line of, it's probably a power problem and the CPU is not getting power. Let's grab our multimeter, and I'm going to check these capacitors here. The white line is positive and the other end is out on the negative, so we want to check from the positive end to ground, which is almost always a piece of copper, exposed copper, or the back end of the cap. You could measure straight across it, or a metal post like that, generally connected to ground. If we just check that to prove, there should be a beep from there to there. It's going to prove me wrong. This one could be out on its own, it may not be connected to ground. If we go that copper to this copper, yeah, so most exposed copper is connected to the board's internal ground plane and so forth, so we will connect. I'll show you the meter. I know that's horrible to see. If I put the light on, it does help, but it doesn't last very long. So if we go negative on the copper ground and positive lead on the capacitor, what does it say? 7.6 ohms, which sounds pretty low. Processors usually around 20, I think, give or take, but 7 sounds a bit low. If we check on the other capacitors up on the right hand side there, yeah, 34 ohms would be acceptable, but 7 sounds a little bit low. The next thing to do would be to turn it on and just see if we have a voltage there or not, and if we don't, we know that that's probably, we're on the right track. Because if the resistance is too low, then it won't create a voltage for it. Let me pull that DC jack off the case. Okay, I'll show you a little trick so you don't have to take your power button off all the time, although if you're comfortable doing that and that makes you feel better, do that. But so you don't have to try and recover your power button. There's a nice easy way to turn these motherboards off and on. So this is ground. And I only know that because it's a nice big section of exposed copper, but you can double check that on the motherboard. But this is the first trace of the ribbon connector, which when flipped over is going to be on the left side. Imagine flip that over and plug it back into the socket. That's on the left side. And then what you want to do is go to the next one and then each one in turn and push the power button, which I've got my finger underneath, and I push that. See, it joins that one to ground. If we try the other two, it doesn't work. So that's our switch. The one that pushing the button connects to ground. That's your on-off wire. So when you go to your motherboard, so you've recovered your charging socket, plug it in, and then you've got your socket that the power button flex goes into. Now I said when you flip it over it was going to be from the left, so the left one is our ground and the next one along is going to be our power button. So all you need to do is with your tweezers join those two together, and that's the same as pushing the button. Just briefly touch them together and the motherboard will turn on. Okay, we are plugged in and not turned on, and we have our white light, so I guess that means charger in. So you just want to jump across those two and then it should have turned on, and we know it has because the power light just blinked at me, so it's doing something. So on here where we had 7 ohms and we have, oh, here we go, that just came up then, so it's like it's trying. So we're at just under a volt. It's probably 0.7, 0.8 of a volt, which I would expect. And if we head on up to the regulator on the right hand side, that's running at about 1 volt. So if it was unable to do that, if that was too low a resistance, then it wouldn't even come up and stay there. It would drop off right away if it couldn't achieve what it's supposed to regulate to. So it's not a good start. What else have we got to check? If we go to the underside, there's another couple of caps which I think are just all working in conjunction with the ones on top. So there we've got one up top there. That's that one that we looked at before, and there's an even bigger one. Unclip my earth lead so I can get a better position on it. Here we go. So that one's on the underside there, so that's 1.2, 1.4 volts. Okay, so we kind of expect those sort of voltage levels around small power efficient circuits like this. I wonder if it's even reading the BIOS. So if it has the ability to create processor rails, then either the processor is dead, perhaps, or something else. So there's our system management chip that monitors our power button and would also deal with a fan if we had one, and many other things. Looks okay around that area. We should see if that has power. I'm sure that one's got power because it's turning off and on and beeping, and that's what the beeping would come from, is that one there, I'd imagine, being the only thing keeping an eye on stuff. Let's check the rest of this board from start to finish and just make sure that there is definitely no physical damage. I now have it unplugged from the charger. Don't know what this does, but it looks like some kind of regulator. Ew. That doesn't look good. A little tiny speck of liquid damage has caused that. And that looks like a switching controller. And why do I know that? Because these appear to be MOSFETs. And we know they're MOSFETs just by looking at them without looking at a data sheet. Because all of one side are connected together, 3 of the other side are connected together, and one of them's out on its own because that's the gate, and then we've got the drain and the source. So that's how you can look at that and just know it's a MOSFET. These ones look okay, but that looks discoloured. Those two look discoloured. Really hoping they haven't gotten too hot. That can lead to trouble if this, whatever caused this, caused the MOSFETs to turn on at the wrong time, and that can cause lots of problems. If we flip the board over directly on the other side, we see, dun, da, 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 here's the coils that those MOSFETs are switching across to create whatever voltage it needs, and guess what? There's our stick of memory, huh? This is very much like the power supply for RAM. So pop the RAM off, have a look at that. That looks okay to me. It hasn't got the RAM wet. What about underneath? Possibly a bit of staining on the board, possibly. But otherwise, no, it looks okay. It looks okay. Maybe it's just a little bit of flux residue from manufacture. So that's going to do it if our RAM hasn't got any power. Although usually there's a different beep code that basically spells out, hey, RAM problem. Got no RAM. Isn't it usually 3 beeps or something? Do we have the same problem? Nope, nice and clean under there. Oh, that's good. Alright. And we've seen that, that's clean. And everything else is clean. And a video connector, charger, battery, input, charger. We'll have a double check around the top side of the board, around the USB sockets, headphone socket. We've had a look at the memory socket already. Here's our hard drive connector. Check out the video connector. Yeah, that's clean. Wow. We might just get away with cleaning up a little spot of corrosion. The only problem is, if it's damaged that resistor a lot, we have no idea what value it is at the moment. We may have to try and guess it, but it's certainly not going to be working too well in that condition. Maybe a quick check of the MOSFETs. Let's just do a quick check. So we've got our multimeter in diode mode, and if I go from the gate with the red probe, I don't know if these are N channel or P channel, but I'm going to assume that one's going to be N and one's going to be P, so we'll get a reading of at least something that looks half decent. So in diode mode, red on the gate, single pin by itself, black on the other pins, that's 0.9 and that's 0.9, so that's absolutely fine. If we switch the pins over, we get 0.5 and 0.47-ish. That's fine. That's not, I mean, they usually fail short. And if I measure across here and here, drain to source, it is actually showing a very low resistance. But as I said, it may not be the MOSFET. See, that one measures okay across drain and source. And gate is okay to each pin. And this one is, it's fine. It's fine. Yep. So I reckon they're all okay. Let's just see what that one is actually across, because that goes through the board. It comes out there between the inductors. Yeah. I wonder where that goes. Ground. Okay. Alright. So that MOSFET switches to ground. And that's the center contact here. So if I go ground, here we go. Okay, so that side's on ground. And across that we measured quite a low resistance. The other side is going to go to a coil which will be fed from a power rail. So effectively measuring across that is the same as putting a probe on ground and a probe on the coil on the other side. And if we take a resistance reading as 300 ohms, it's not down at near zero, which a shorted MOSFET would show, but in diode mode it's low enough resistance to show what looks like a bad reading, so I'm going to say that's fine. And hopefully our control IC is fine. Should we see if we can get a data sheet on that, and then we'll know what that pin is doing, that resistor, both of those resistors go to. It might give us a better idea as to the function and the fault that's going on. I think they're actually joined together. Or does that go to that through hole? Okay, it goes to that through hole down there. Probably find that the solder joints have gone so bad on the ends that they're not making any contact at all. It's like magic. All we need is a little alcohol and everything's better. No, it's not better. Not yet, at least. Is that 1225C? 1225C or T? I think it's a 1. Back at Google, and we chuck in 1225C data sheet. Look at that. Right away we get a result, and it's a Texas Instrument part. Dual synchronous step down controller, 5 volt and 3.3 volt. 5 and 3.3 LDOs. Okay, so this is able to produce both rails, and that's why it's got 4 MOSFETs off it. 2 MOSFETs running one inductor, 2 MOSFETs running the other inductor, one creating 5 and one creating 3, and it won't make much at all if it's got corrosion around it. So let's have a look at the pinouts and what's going on. Pin 1, they've kindly marked the board for us with a white spot, but if you get it in the right light, there's a little circle in the corner. That's pin 1, which is this pin here, and it's counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. And we're looking for pin 4 and 5 go to our damage. Pin 4, VFB2. Now, who's going to tell me what VFB would probably stand for? How about voltage feedback? Let's have a look down here. Oh, voltage feedback input. So it needs to know if it's making 5 volts or 3 volts, or if it needs to try harder or try less to maintain that voltage. So this is our feedback pin, and that's going to allow it to know what it's doing. And of course it was full of corrosion, so it couldn't get that signal. It doesn't know what's going on, so it's not going to create the rail properly. And CS2 is, here we go, sets the channel to OCL trip level. Okay, channel 2. So channel 1 would be, say, 3 volts. Channel 2 would be 5. I don't know if that's how it is. I haven't read the data sheet, but that's how it's going to be, give or take. And trip level. So trip level is going to be what, over voltage? Let's see if we can find more about what the trip level is. The CS whatever, in our case is CS2 pin, should be connected to ground through the CS voltage setting resistor, and that's the resistor that had corrosion on it. So the trip voltage is going to be a something to do with the resistor value multiplied by ICS, which is the pin source current, which is 10 microamps typically at room temperature. Okay. Divided by 8 plus a millivolt. Okay, so here's our table. It tells us that channel 1 is 5 volt and channel 2 is 3 volts. Let's see if we can figure out what that resistor should be then. What that value should be. I hate doing math at 10 to 10 at night. Oh, my brain hurts. Sometimes looking at a picture can help. Sometimes the manufacturer will copy to copy everything, every value almost. In the example circuit layout, design layout, because why not if they've already given you the answers. And here's our 3.3 reg, 3.3 volt reg, and it says CS2, it should be 47k ohms, and the pin 4 feedback was, I've got 10k to ground, that's ground, that triangle, and 6.5k up to the inductor. So I think it's our ground resistor. So let's see if we can do a quick check and see through the corrosion and maybe try and get a reading as to what those resistors are. Instead of putting a probe on the corrosion, I'm going to stick the probe on the chip because it's nice and clean. And then this is a nice clean side of this resistor. And what are we getting a reading of? 84k ohm, which is interesting because it's always going to read a bit lower in circuit. And then if we do the one beside it and see if we can get a bit of shiny corner of that there. I scratch through the corrosion very gently and get a reading. Maybe, oh, nearly. We've got 5k ohm. Let's just try a bit more. 5k ohm off pin 4. And, well, that was 10k to ground, so that could very well be 10k in circuit. It may show up as 5. I wonder, let's just see if the other side of that resistor does go to ground. No, that doesn't go to ground. That's let's hit it with some flux and hot air and see if we can clean off that corrosion a bit and hopefully reuse those parts. I know, as I could have just done that to start with. I'm sorry. I totally didn't push record on that one. Just put some flux on there and hit it with some hot air. I used a low air speed so I didn't blow all the flux away, so I was at 50% air and about 370 Celsius, just so the flux would bubble around and do a bit of cleaning for me, and it did clean up somewhat. So now I'm going to hit it with a solder iron and see if I can freshen up the solder on each end with some nice shiny new solder. You could have just done that to start with, but looking at the data sheet and trying to understand how things work is all fun. The one on the left, however, is a lot worse for wear. Roll the Q-tip and it helps drag all the hairs away, all the fine leftover fluff. This is why this is a problem. The end of this resistor is not shiny like this one. All of the metallization on that end has been eaten away, and it looks like the other end as well is pretty much gone. And the problem with that is the resistor is the black coloring on the top. Now, have I got one I can show you? It will give you an idea as to what I'm talking about. You can see on the top is the black, that is our resistor, and on the ends are metallized coating that connects to each end of that piece of carbon, which sets the resistor value, and then the solder sticks to the metallization. Now that's all been chewed away, which means the solder can't stick to it, and all that's left is the body of the resistor, which is just that white substrate, whatever it is that they use. You can see how the metallization wraps around the end so that you get a nice solder connection on the bottom. With all that end eaten away, it ain't gonna work, and I'd say that's what we were getting a bit of a false resistance reading from. Now I've soldered up the other one. That's doesn't look too good at that end. Let's just recheck the resistance across there out of curiosity, and I've got 185,000 ohms. So there's our pin 4. That pin 4, feedback 2, goes to 10k to ground. Pin 2, which is also feedback, goes 10k to ground. It has a different resistor on the other end, as it should, because it has to generate a higher voltage. But the CS pins are a little different from each other, so what we need to do is have a look at the good ones on the other side of the chip. Well, they're on the same side, weren't they? Pin 1 and pin 2. Let's have a look at those, because they weren't chewed up with corrosion. And that resistor is going to be the same as that resistor is going to be the different one. So pin 2 is our feedback, which should have a 10k to ground, and measuring that is not 10k to ground, which is 200k in circuit. I think they may have the difference between the two is possibly, oh no, it's 178K and 200 and something K, pin 1 and pin 5. They've obviously used different values, but the ratio of the values is probably the same. The model of the board is LA-B481P, and look what I found. We need to find PU100 is what they've labeled it on the board. So if we zoom in, do a control find PU100, there it is. So much wait, where are we? Come back. So much time saved. Oh, zoom in, where are you? There you go. Let me like zoom out again. Wait, this is no good. Let's open it in Adobe. There we go. PU100, a lot easier to look at. Right. So pin 4 and 5, and it should be, oh look, 187K ohm. So that was pretty good. And pin 4 up here is 20K ohm. And then a 13K ohm to the inductor. So we better find the right resistor, because there is a couple of resistors involved, one to ground and one to the inductor. And just having a look at that, if we can't measure one end to ground, then we need to find the other. Well, that's not the resistor we're looking at, so go to ground and probe on the end of the resistor. Okay, so that definitely is ground, and that one there, that's not ground. So the pin 4, I don't have a direct path to ground, so I think it could be the 13.7K ohm. 13.7K. You can see where the metal has worn off the end of that I showed you, but if I stick a probe directly on the end of the black carbon, which is our resistor, I'm getting a reading of 13.8K, 13.7K. If I probe the solder pad at the end, which isn't connected, I'm getting 15.6. So that resistor is our 13.7K, which is the one on top, and the one beside it is our 187K to ground. So we can leave that alone because that still measures. There we go. Put positive on the right side, put negative on ground. There we go, 180 odd K to ground, so that's fine. I need to find a 13.7K ohm in a tiny little package. It's good to be sure. If we have the wrong feedback on there, it ends up cranking higher voltage through our 3 volt line. 3 volt ALWP always present, I suppose, I don't know. Oh look, here we go, and here's our equation for working out our overcurrent protection. Going through my junk trying to find a resistor, not easy, but this is where I'm at the moment. I have a MacBook motherboard, model 820-3115, and we're looking for a 13.7K resistor, and this is what I've been doing amongst a couple of different models until I got to this one, 13.7K, and bingo, there's our 13.7K. And what's interesting, if we scroll down and see what it's connected to, it is a dual voltage buck converter. So and it is a TPS, TPS 51125, and the one in our board is a TPS 51225. So I don't know what the difference is between the models, but
it's obviously similar enough that we have a it's obviously similar enough that the Mac is also using it for what do we got there? 3v3. There's our 3v3 over on the right hand side there. And if we zoom out and have a look on the left hand side, 5 volt 5vs3 is the one. There we go. Because that's off the end of the inductor here. Right. I wonder what they're using for the resistor to ground. Is that even off the same pin? 13.7k is coming down to ground, and the other end is going down to pin 2. So they're using that value for the 5 volt side of the reg, and whereas we are using that value on the 3 volt side of the reg. There's a 10k here. Not going to complain. There it is, resistor, and it is R7268. So now we have to go to find that on the board. We can use open board view and find Control F R7268. Zoom out, and it's there. With the RAM socket up there, there's the chip, and there's our resistor. Lucky it still exists on this board. Let's go have a look. 1, 2, 3. Third one up on the right of that whole row of resistors. And there we go. Third one up on the right is that one there. I've got a couple of these boards. If I accidentally flick it across the room, never to be seen again. Oh, good. It's the right size, if not a touch smaller. No, that's what I was going to do. Is it? 13.7k. Yes, it is. Excellent. Let's try this at a different angle. Okay, so here we go. Our inductor on the left is our 5 volt one, I believe. That's the 100. No, 100 is 3. Inductor on the left is 5 volt, and inductor on the right is 3 volt. Let's see if we have 3 and 5 volts. There we go. We have 3.3 there. And on the other side we have about the same. Where's my 5 volt? 2. Oh, hang on. 2, 4, 5. Sorry. Yeah, we have 5 volt there. And we have 3.3 or point something. Alright, well, it appears to be running, and I've got some heat in the heatsink of the CPU. So now all we have to do is put a screen on it and see what's going on. We may have solved it. It hasn't beeped at us, so cross fingers. Alright, and I'm hitting the power button now. We still appear to be getting nothing. Of course, the thing is, we don't know that that rail was not making power. And so we don't know, we should have tested it perhaps instead of just fixing it, what we found is bad. But we don't know, that may have been actually working even though it looked bad, and that wasn't our fault. Let's just let it sit there and see if we get our beeping noises. Yep. What do we need to do is check all of our other power rails and make sure that they are all working, I think. So here's a list of our rails. We need to go through and check that every single one of those is present. Well, we know we've got power coming in because most of our rails are present, so I'm going to skip that. RTC, battery power, real-time clock, that's going to be okay, I think. But let's just do the exercise. So let's look for RTC VCC, and if we do a search we come to here, and that is that's our real-time clock. And of course we've got our backup battery comes in through here through this twin diode package, and our charger power also comes in through here, so it's got power when it's plugged in. DC3 is the diode we're looking for, so we may as well go to the battery and see if we can find it. And sure enough, it's right beside the battery. Here's our battery. Here's DC3 at the top. So we'll have a look. We've got our power plugged in, and we should have, what do we got there? We've got 3 volts. We've got battery voltage there, and on the other side we've got 3 something volts as well. And in the middle we've got our 3 volts coming out. Next is our 1 volt always on. So let's copy that. Find 1 volt always on. And that comes from PU301. So we've got to find PU301. There's a inductor involved. So it's a buck regulator. It's switching down from a higher voltage, which is our 3 volt always coming into here, so it should be putting out 1 volt always. Let's find PL301, well, PU301 is the chip that runs it, so it's going to be a small one. There's our fan shield, our missing fan shield. Oh look, that's where they would have had a fan connector. If it did have a fan, you could probably maybe populate that stuff and see if it works. Anyway, interesting to see what the schematic says there, if it says no stuff or what. But here's PU301, which is this little regulator here, and there's the coil for it. It's just a very simple one, and if we probe on the end of that coil, what have we got? 1 volt. 1 volt there we go. So our 1 volt always is present. 1.8 volt always, find that one. And that's going to be from PU400. Here's our PU400, just over from the 301. Pop a probe on the end of that, and we got 1.8 volts. Our 3 volt always, we know that's there. We know our 5 volt always is there because we just fixed that if it was even broken. 1.3 volt DDR. Now that's on. It's not on at the moment, so we're going to have to now, because we're in a S4, S5 state, which is in an off standby state. So now we're going to have to turn the board on. What do we want there? DDR 1.35 DDR RAM. Okay, that's not it. So we have our 1.8 and 1.3 volt supply IC, and it looks like there's one that does 5 and 3 volt for a separate system there as well. So U59, that's what it looks like. Well, I found U11, and that's exactly what I thought this IC would look like. And U11 is the chip that it's identical. It's an identical chip. So we've got U11 that does 3 and 5 volt, and U59 which is configured differently. It's the same chip but configured differently to create different voltages. So here's U11, and you would think that one of those, which is quite a unique shape to all the rest on the board, would be just jumping out, and you wouldn't miss it, except it's not. Here is the chip that creates 1.35 volts. Not the one I was looking for. So this is PU200. Just along, so these are the inductors for our 3 and 5 volt rails, and this one is not far from it. PU200. What pin am I supposed to find for that one? Switching an inductor, which is inductor called PL200, is it? Yes, I can measure off the end of that. What do we got going on here? 1.35, there we go. SOC VNN. So that is PL500, which is the other inductor. Which is fine, sitting just below 1 volt, which was the other capacitors by the CPU that we had a look at earlier. So we know we're good. 0.675 volt. That's our DDR3 terminator. Oh yeah, okay. There we go. So back to our PU200, and we want to look at pin 20. 1, 2, 3, 4, 5, 10, 15. It's going to be the top one, which is there. That looks like 0.67 odd to me. We've got a 1 volt system power rail. Where is U60? That's what we need. U60 is just a MOSFET. We should have a 1 volt signal on both sides of that. Back over to where that other regulator we looked at earlier. There's U60, right by the heatsink shield to the processor. So if we have a look, we should have a volt signal on there. We have 1 volt. Let's just check the other side of that FET, since it seems to be switching it through to places. Make sure we do have it on both sides. Here we go, 1 volt on both sides, we're happy. 1.05 volts. PU300 is the creator of that. This is over by there's our clock backup battery, and there's PU300. And checking PL300. There's our output inductor, sorry, and if we stab at that, there's our voltage. Now next one is our 1.35 volt UC7. It's only a small package. UC7 for the RAM. Okay. UC7 LR2. There it is. UC7, right beside our WinBond BIOS ROM chip. Right, take my word for it. Moving on. 1.5 volt. Copy. Find. We can check for that. No, I'm not going to go looking for that. 1.5 volt SP. Oh yeah. Let's look for PU402. PU402, which is down from the battery, not too far down from the battery. And there's 1.5 volts. 1.8 volts. Copy. Let's see if we can find UC10. That should have 1.8 VS on it. And for the record, we want pin 5. One, two, three, 4, 5. What have we got? 1 point, whatever we're looking for, close to 2. It was 1.8, wasn't it? There we go. 3 VS. Well, that's probably present, but let's just do it anyway. Pin 4 on one side of a resistor to pin 4. So staying in UC10, pin 4, there's a resistor across there. So let's just have a look at that. And that was that resistor 1, 2, 3 point something. Hey look, I found U59. It was hiding between those two connectors. Ah, it's good to know it was here all along. And it's creating 2 power rails. And I'm just going to see if they exist just because I can. There's that one there, 1.3, and the other one which is 1.8. Good. There we go, plus 5 VS. That's U11. That's the one that I could find up over here. Okay, I'm going to run with that, and we want, this should be creating 5 VS and 3 VS. Created independently. 1, 2, 3 and a bit, and the other one went off scale, so that's going to be 5. Let's go like that. Here we go, 2, 4, 5. Great. Not great, but all of our rails are present and correct, which means this has other more serious issues. Like, what could it be? So now we've confirmed all the power rails are present, and the all the ICs, the processor and the SMC all have the signals, the power that they need to operate. So what we're going to do is see if it's brain dead, and I like to check the ROM where the BIOS is held, and see if there's any data transfer when we turn it on. And if not, then we know it's a bit brain dead. It's not even trying to boot up and do a post power on self test. So let's do that. Our SPI ROM chip is pin 1, data out pin 2, and clock and data in is 6 and 5. So I mean 6 should have something even if there's nothing coming out of it. that maybe it's a bad ROM. Maybe it's not booting. If there's clock and SPI MOSI, I would expect something coming out. I think that's how it works. And then I will hit the on button. Why did that come on? Didn't even turn it on. Let's try turning it off again. Maybe it came on in some weird state. Oh. Okay, well, we'll assume that's standby and it's got power on it. I'm just going to get you out the way so I can see where I'm going with the tweezers. Turn it on and the drops. Power light blinks a couple of times and then nothing happens, and then it goes back up. It's interesting. Oh, and then it comes down. It goes up. Let's change our time base there, see what's going on. And back up. Yeah. Interesting. I wonder if we're missing an event of any sort there for the trigger. Let's just AC couple that. A whole lot of nothing going on there. Okay. Let's see if our clock circuit is operating, because if we have no clock, the processor is not going to be able to execute commands. So where is our clock? RTC, there's our clock power, and we've got clock reset. Suppose it could, the CPU could be held in a reset state as well. Here's our crystal for our oscillator, so we need to see if that's working. There's our CPU, there's our oscillator, and I'm going to probe on each of those. Up the top there's two little capacitors, one on each end, and the center is where our signal should be. And I'm going to be very, very quick about it. I'm going to switch it on with the holding the scope in place so I can catch it if it's working, and then I'll pull the power off almost immediately because we don't want to blow the thing up and overheat it. So yep. Okay, here we go. Yep, cool. You saw that. We have a clock. So we have clock, we have power. I'm pretty sure if something is held in a reset state, that the clock stops oscillating. So I don't believe it's being held reset. Pin 100 is our reset out. 98, 99, 100. And she's off the charts, boy. There we go. That's a high. That's not reset. Platform reset. What if, okay, what if the EC is being held in reset? EC reset. Pin 37. EC reset. Let's have a look at that, shall we? 33, 34, 35, 36, 37. Off the end of that cap. No, that's not being held reset. Maybe I should have Googled a bit more than just that Dell Inspiron 7 beeps. Let's see. Wrap it in a large towel, leave it on beeping, but wrap it in a large towel. So overheat it and it might work again. What does that tell you? That says bad solder joint / bad processor, bad die connection, bad flip chip die connection. Cool. Okay, so another list of beeps says it's a CPU cache test failure. Oh, that's on board the CPU, isn't it? 7 beeps. Reseat or replace the CPU or motherboard. Should we hit this processor with some hot air? See what it does. I think that's probably our only option. 7 beeps of death. Dell community. What does that tell me? Blah 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 blah. 7 beep codes indicate a processor or board failure. Well, okay, I'm going to call it. We've got everything we need for this to work and it's not working, so I'm going to call it.
We'll try not to popcorn the thing. I'm just going to let it get hot. I really don't want to float it, really don't want to bake it. Let's just get it nice and hot. And I'll be at 380 Celsius at some distance away, so you won't see it. I'm going to be quite a distance away. It's going to be probably 50 mil, good, maybe 6 centimeters away, just to get a good airflow over everything. I mean, even at that distance I can't touch the board already, so that's pretty hot. So we want to let it soak in, let a good amount of heat soak in. Yeah, I can't touch that. Just let it soak in from a distance. Yeah, I'm going to take that battery out. Yeah, don't have to think about it at all. There we go. And I probably, in all honesty, like, I really don't want to float it. So I should probably remove the edge bonding, just in case it does decide to float on me. Just peel that little glue off from the corners. We don't really want to heat one spot longer than another spot. We just want to get it nice and hot, because this little square on the top, that's our chip, which is flipped upside down and bonded to the large green base, and it's the bonding between those two that apparently suffers. And if we get it nice and hot, then they say that you can soften the glue and cause the bond to re-adhere, but we'll see. So we must be approaching fairly hot on the surface by now. I've come in a bit closer there, just spreading the heat out. I'm trying not to let it cook any one particular part more than another. Just hover over the center for a little bit, get that die nice and warm. And we'll call that, shall we? Let it cool down. I bet it won't work. I'll jinx it right away. Alright, our charging light came on, so that's a good start. I reattached the power button because I got sick of using the tweezers, so here we go. Still nothing. Let's just see if we've got our power rails, because the charge light didn't go off like it did last time. It blinked at us last time. So do we have a... yeah, we got a rail there. We've got a rail there. Well, I'm going to call that a complete failure. It's obviously the process is bad. We couldn't get any data activity on the ROM chip, and it's still beeping at us 7 times. They say online CPU, not the motherboard. All the power rails are there. I really don't think it's the motherboard, and as I said, no data on the BIOS, so it's not even trying to boot, trying to post. Well, I hope that helps you follow schematics, and maybe you will figure out how to fix a board that's not a dead CPU. But in this case, we didn't get lucky. Well, thanks for watching.